Hello, everyone. So today we're going to be focusing a little bit more on the process of mixing when we look at mixtures and seeing what this can tell me about the favorability and kind of the energies of these sort of systems. And hopefully, though, it might be a little bit more energetic than this. Well, a little less energetic than this. So when we're trying to start examining the mixing of species, a good place to start is going to be with gases, mostly because gases are fairly well behaved and they're going to have very minimal interactions. So, specifically, we're going to start working with ideal gases. And one of the reasons why ideal gases are going to be so nice is we don't really have to worry about any influences of intermolecular forces. And we have one of the world's simplest equations of state with the ideal gas law. So if I'm essentially going to be looking at how two gases mix, a good assumption is that I'm going to go ahead and start by taking a box where I have two separate gases in separate sides of the container. So I have, say, gas A on the left side of a barrier and gas B on the right side of the barrier. And each one of these are going to have essentially allowed to come into thermal equilibrium, and essentially I allowed this barrier to be movable so that they're going to also have identical pressures. However, I'm not going to guarantee that they're going to have the same number of moles of species. So I may have more A or more B, just like I will with any sort of mixture. So this allows me to vary the concentration of my effective system by essentially varying the ratio of these two species. And because they're ideal gases, this means that the two volumes will also be different. Then, in order to mix the species, all I'm going to do is remove the barrier and allow both of the gases to expand into the new final volume. So if I am, say, looking at A, what's going to happen is as I remove the barrier, the volume is going to end up expanding into this new final volume. So I no longer have a volume of BA, instead I have the new total volume V. And similarly, this is going to happen with the volume of B. You add them together, and my new total volume is just going to be the sum of the previous volumes. However, it turns out that as the volume of the sample increases, we're also going to see a pressure drop. So as the system expands, the pressure is going to correspondingly drop. And so then I'm going to define A by its partial pressure, or PA. So this is going to be the pressure just associated with my new expanded A, and similarly for PB. However, because of the additive properties, as the volume ends up expanding, what's going to end up happening is that the sum of these two pressures is going to still give me back my initial pressure. Because another way of thinking about it, my total volume didn't change, my temperature didn't change, and my total number of moles didn't change. So as an end result, the total pressure has to be the same as it ended up, as it started. It's just more about how it's divided. So if I'm going to try and examine the favorability of this mixing process, I'm going to need to take a look at Gibbs, because Gibbs is going to tell me everything I need to know about how favorable a reaction is. However, to keep things as simple as possible, we're going to want to start by looking at the chemical potential of each individual components and using this to inform us what we know about the Gibbs. So if I'm, say, looking at just side A, well, the chemical potential of this system can simply be given by the standard state chemical potential of A, say at 1 bar. And then I go ahead and correct it for pressure, as we've already seen with the pure species, of RT natural log of the partial pressure of the pressure of A over the reference pressure. And again, this may be the vapor pressure for the final state or the total pressure for the initial. Now, if I'm going to be looking at the Gibbs free energy of reaction, I'm going to have to take a look at the initial free energy and the final free energy. So if I'm looking at the initial free energy, well, it turns out that, as always, the free energy of a mixture can be given in terms of the chemical potential of each of the individual components times the number of moles of each of these species. So what we can then do is say, insert our equation for the chemical potential of each component into this expression. And so what we end up doing is we end up generating an expression with the essentially free energy under standard state of A, plus essentially our pressure correction. And again, our initial pressure is just going to be the same as the total pressure of the system. And under these initial set of conditions, both A and B will have that same pressure. Again, the only noticeable difference is going to be a change in the reference chemical potentials and the amount of each individual species. However, in order to get an idea of the mixing, I have to go ahead and see what's going to happen with the final free energy. So in the final case, we're going to see a very similar expression, but the only thing that really changed is the pressure. Because it's a closed system, so the total number of moles of both A and B is going to stay constant, the identity of the species won't change, and it stays in the same thermal equilibrium. So the only thing that ends up changing is we watch a pressure drop. So in order to try and get at essentially how favorable this mixing process is, well, this is just another kind of reaction. So I go ahead and just simply take final conditions minus initial. So if I do a good old-fashioned final minus initial, this is going to give me my free energy of mixing, or essentially telling me how favorable the whole process is. Now, what you're going to notice is that, first of all, the reference conditions don't change in the final and initial state, so they'll essentially just disappear out as a sort of reference condition. And then if I look at system A, you'll notice they share a same prefactor of nRT, and so what we have is ln of PA minus ln of P. Well, we use our good old friend, the log laws, and we get the natural log of the ratio of the partial pressure of A, also known as the final pressure, over our initial pressure of the system. And then we have an identical expression for B. And so really what this is going to be telling me is that if I were to treat my gas as a pure system, the change in free energy is going to be entirely related to the extent of the pressure drop. And it's going to be the pressure drop that drives mixing as being favorable or unfavorable. However, one of the other pesky parts about this process is we now have two pesky variables in front here in terms of the moles of A and the moles of B. And in truth, let's be honest, we like size-extensive variables a little bit more. So we're going to try and replace our moles of A and B with the mole fraction. And as long as we're at it, turns out the ratio of the partial pressure to the total pressure is also our original definition of the mole fraction. So what we can do is substitute in mole fraction for both the ratio of pressures, where this is going to be the mole fraction of A, and this will be the mole fraction of B. But as long as we're at it, we can also express the moles of A as the total number of moles times the mole fraction of A. So by doing this, what we have is the total number of moles in the system, so moles of A plus moles of B, times the mole fraction of A times RT, which is going to be a constant, times a system-defined variable, times the natural log of the mole fraction of A. And again, similar correction for B. Now, because let's be honest, we often want to get rid of variables, one of the things we can do here is substitute out mole fraction of B for mole fraction of A. That way we can define the entire property of the system just on mole fraction of A. In addition, remember this is the size-extensive Gibbs free energy of mixing. In order to turn it to a molar property, you can divide both sides by the total number of moles, which is a fairly useful trick when dealing with large systems such as an atmosphere. And so when we actually plug in all of these relationships, we actually get a fairly cool feature of the Gibbs free energy of mixing, because it turns out that it's largely going to be driven by this mole fraction of A times natural log of the mole fraction of A. Now, one of the very cool features of this is that it turns out the mole fraction of A can't be negative, so it has to be a positive value, but it also can't exceed 1. And because it's limited to a value less than 1, that means that the natural log will always be negative, and the prefactor is always going to be positive. So this means that the Gibbs free energy of mixing for both A and B are going to always be are always going to be negative, which indicates that no matter what the mole fraction of A is, so no matter the composition of our system, for an ideal gas, mixing is always going to be favorable. But one of the things that's worth noting is that this system will essentially be the most, will end up having the most negative value, as essentially I try and keep the system as positive. Essentially, this whole term is going to have the most negative value when I'm able to maximize the natural log term on both sides. And this is more or less going to end up happening when I get a natural log of 0.5 and 0.5. So it turns out that the most favorable free energy of mixing always happens with a 50% mixture of both species. So this means that if I'm going to take a set of complexes and find the point that they are going to be considered the most favorably mixed, it's when they are literally a 50% mixture. 50% A, 50% B will always be the most favorable mixture combination when dealing with an ideal gas. But this leads us to another important question. If mixing is always going to be favorable for an ideal gas, why? And one of the things that ends up showing up here is that it turns out that because I have an ideal gas, this means that there is going to be no enthalpic contribution, because enthalpy means that I've got intermolecular forces hiding in there somewhere. It's an ideal gas. There is no intermolecular forces, which means that all of this interaction has to be driven by entropy. And we can actually prove this by essentially making use of one of our old relationships, which is that the entropy of a reaction, or any entropy, is going to be equivalent to the negative of the isobaric change in free energy with temperature. So again, a good old throwback to our fundamental equations. Now, it turns out that our energy of mixing has a linear relationship with temperature. So when you go ahead and take the derivative with temperature, all that ends up happening is you're going to flip the sign and get rid of your temperature term. So it turns out that the entropy of mixing for an ideal gas is going to be related to the number of moles, the mole fraction of A, and again, corrected for units by our good old friend, the ideal gas constant. And again here, because mole fraction has to be somewhere in between 0 and 1, we're going to have a negative expression from the natural log, but now we have a negative prefactor. So this means that in total, our free energy of mixing is always going to be positive, and it's always going to essentially max out at a value of 0.5. So turns out that mixing is entirely an entropy-driven process, at least for an ideal gas. Now, in truth, things can get a little bit messier as you move to non-ideal systems, because then you have to worry about the influence of enthalpy, and that will essentially show up in non-temperature dependent terms. However, for gases, this is actually a fairly good approximation. However, there's a world of systems beyond gases. So next time, we're going to start by focusing on liquid mixtures with a specific emphasis on those that are a little bit better behaved and act a little bit more like an ideal gas. So until next time, take care.